The break is over. I made some coffee. And let's go. So let's see the definition of convergence in probability. We say that a sequence xn of random variables converges to a random variable x in probability, and we denote it in this way. If for every epsilon greater than 0, we have that the limit over n of the probability that xn deviates from x for a value larger than epsilon, this probability goes to 0. What does it mean? It means that as the sequence increases, as the sequence gets into larger and larger indices, so for example x1, x2, and so on, when we get very far in the sequence, the probability that it gets close to x, to some value, is 1, in the sense, well, this is equivalent to say that the probability that the limit of the probability xn minus x is less than epsilon is 1. For example, so how can I try to explain this better? We have a sequence of realizations. Well, here we don't consider the, well, in some way, yes. But this time we focus on the probability, not the value itself of the random variable. The value of the random variable, as we may see in a further example, in the next example, the values can be very, very large. I mean, this, for example, xn can be 1 million, and x can be 0.1, but the probability that this happens goes to 0. So the main focus here is probability. I don't know if this is somehow clear. So here we have a remark. For almost sure convergence, you look at the limit of the sequence of realizations. So we look at the sequence of realizations. And after that, you look at the probability of the set in which this happens. While in for convergence probability for each n, you evaluate the probability that xn is distant, but by at least epsilon from x. You evaluate this probability, which is a sequence of numbers, and you look at the limit of this sequence of probabilities, and if the limit is 0, then x converges in probability to x. So we can have that the distance xn minus x is very large, but the probability is 0. This probability goes to 0. Okay, this was a bit better explained, but the idea should be the same. And let's take a look at an example which illustrates that convergence in probability does not imply almost sure convergence. So consider the following samples, the following probability space. We will take omega hp to be the interval 0, 1, the closed interval 0, 1, the Borel sigma algebra on the interval, and the Lebesgue measure. And now consider x1, x2, and so on the indicators of the intervals 0, 1 with 0 open and 1 closed, then 0, 1 half, 0, 1, no, now 0, 1 third, 1 third, 2 thirds, 2 thirds, 1. Shouldn't we have here 0, 1 third, 1 third, 2 thirds? Yeah, my question, shouldn't we have 0, 1 half, 1 here? Then, for any epsilon greater than 0, with epsilon taking values in the interval 0, 1, the probability that xn is larger than epsilon forms the sequence which is 1, 1 half, 1 half, 1 third, 1 third, 1 third. Why? So the probability of this is 1. The probability of this is 1 half, the probability of this is 1 half. So yeah, we missed here in the note. I should correct this. Half 1. General formula for this. Let's say, I don't know, I should take some more time to reflect about it. But in any case, we have that the probability, why do we have larger than epsilon? Well, it may simply be a formality. Sequence goes to zeros and goes to infinity. And hence, hence xn converges in probability to 0. So we considered these kind of indicators, and for any epsilon greater than 0, why do we have this? But we take a look at the sequence of probabilities of being larger than this epsilon. Okay. So this implicitly means that the probability that xn deviates from 0 from a value larger than epsilon, so this is the implicit formula, let's say, or expression. So this sequence converges in probability to 0, but it does not converge almost surely, because, however, for any omega in the sample space, xn of omega is it is 1 over n. No, it is 1 or 0. Why? Because they are indicators. Because they are indicators, therefore, the limit of the sequence xn is 0, while the lim sup is 1. And this implies that we cannot have almost sure convergence. We can have it. So we don't have almost sure convergence, which means the set omega 0 is empty. Okay. Now let's see the characterization theorem for convergence in probability. If xn converges to x almost surely, then it converges in probability as well. If xn converges in probability to x, then it has a subsequence which converges to x almost surely. And third, if every subsequence has a further subsequence which converges to x almost surely, then the sequence converges to x in probability. Let's take a look at the proof of point 1. Let xn be a positive sequence of random variables for any n. And x equals 0 be the limit. And this is not a special case because you can replace xn minus x in absolute value with x. It says here at least. Now recall that I epsilon plus, now recall the definition of I epsilon. Well, here it is written epsilon plus infinity. And define Pn as Pn depending on epsilon, which is I epsilon applied to xn, which is basically the probability that xn is larger than epsilon. We know that xn converges to x in almost surely, in the almost sure sense, so we can fix epsilon positive. We have that I epsilon applied to xn is, well, goes to 0 almost surely. Correct. And now take the expectation we have that Pn is the expectation of I epsilon applied to xn, and this should be, this goes to 0 as n goes to infinity. Which means the probability that xn is larger than epsilon is 0, right? Or goes to 0. Goes to 0. And this implies that xn converges in probability to 0. Let's take a look at the proposition related to convergence probability. Consider f from R to R continuous. Then, if xn converges in probability to x, also f of xn converges in probability to f of x. Proof. Assume xn converges in probability to x. So if we have this, we have to prove this. And, well, let n be a subsequence of n star. Of the positive natural numbers. Then we have that x capital N converges in probability to x because of the previous theorem. For point 2. Of the previous theorem. So there exists a subsequence xn prime, x capital N prime, along which xn converges to x almost surely. From now on I will write as dot simply, which is faster and more comfortable for me. Then f of xn of omega is f well, it should be x of omega should be f of the limit of xn of omega, I think. And by point 3 we conclude that f applied to xn converges to f applied to x. Sembra un po' una scammata. It looks a bit like a scam here. And another remark that we have is that convergence probability is preserved under arithmetic operations, which means that, for example, if we have a sequence xn convergence, if we have two sequences, one is the sequence xn converging in probability to x, and the other one is yn converging in probability to y, we have that the sum of the sequence of random variables xn plus yn converges to x plus y, and so on for the other operations as well, except in the case in which we have the division, I think. Because 0 gives problems usually. Now metric convergence for convergence in probability. Now, okay, let's write it in this way. Metric for convergence in probability. Introduce the distance between two random variables to be the expectation of the difference, absolute value. what is this? I think this is correct. The proposition here says that xn converges in probability to x if and only if the distance between xn and x, so the expectation of the difference goes to 0 as n goes to infinity. And we will prove an alternative version of this proposition, which is the following theorem. Which we will see next time, basically.